Okay, so we are ready. So our next speaker is Dr. Syksy Räsänen from University of Helsinki, and he will talk about the gravity track of Higgs inflation. So, Professor, the screen is yours.
Thank you. Thank you for the invitation. So I'll be talking about some work related to the idea that the standard model Higgs could be responsible for cosmological inflation, and some of the people I've been doing this work with are listed here. Let me just begin with a bit of sort of philosophy or motivation for this. So before the LHC was turned on, it was widely expected that physics beyond the standard model would show up at the electroweak scale and would be seen by the LHC. In fact, this was widely expected already at the Tevatron at Fermilab, and before that at LEP2 at CERN, before that LEP at CERN, and before that UA1 at CERN. And none of these experiments has seen any such physics, and the constraints have just been getting stronger and stronger. And also, there was an idea that dark matter would be these particles that have weak scale masses, weak scale interactions with themselves and with standard model matter. And this possibility has been ruled out by direct detection experiments. They can still have maybe weak interactions among themselves, although this possibility is already more and more constrained by indirect detection experiments. So this has then raised the interest in the possibility that, in fact, there is no physics, new physics close to the electroweak scale, and maybe there is no new scale above the electroweak scale at all, apart from the gravitational scale. So maybe one should take the standard model structure and the standard model matter content more seriously and see what can be done with that instead of thinking about possible additions. So this Higgs inflation is sort of in line with that philosophy. So here we have so here is part of the standard model action. This H is the Higgs field, so we have the canonical kinetic term. We have the Higgs potential, which for large field values goes like the field to power 4. And then we have here also the gravitational action. So we have the Einstein-Hilbert term, the Ricci scalar. And then if we combine these, so if we take the standard model and we take gravity in curved spacetime, then there is precisely one term that can be written, one term that can be written down when we have both of these actions that we cannot write down with them individually. That is dimension 4, and that is this term 𝐸H²R, where Xi is a constant. And so from the point of view of vector field theory, I mean, we should have this term. But even if you don't have it classically, when you renormalize in curved spacetime, then to get rid of the divergences, you must have this term in the action, this term in the action. And of course, it will run. So if you put it to 0 on some scale, it will be non-zero on some other scale. And then in 2007, it was realized by Fedor Bezrukov and Mikhail Shaposhnikov that if you have this term in the standard model action, then you can use Higgs as the inflaton. So using the fundamental scalar field that we know that exists without adding any new degrees of freedom. So let me first then now discuss a little bit this the Higgs inflation. So how does it work? And then how does it relate to this topic of gravity and different formulations of gravity? So let me start there. So there are different formulations of general relativity. And they are not modified theories of gravity or extended theories of gravity, but they're really, so they're not sort of that you have one branch or one root and trunk, and then you have different branches, but rather you have different trees. In the sense that they are not, well, let me explain what I mean. In particular, the Palatini formulation, so this is the one of the most studied alternative formulations of gravity, so that the metric and the connection are independent degrees of freedom. So in the metric describes distances in space-time, and of course then inner products of vectors, and the connection says what are the straight lines in space-times and gives you derivatives of vectors. And a priori, on a general manifold, the concepts of distance and straight lines are completely independent. So the metric formulation of general relativity, which is the first formulation discovered by Einstein and Hilbert in 1915, so there the connection is Levi-Civita, so everything is given in terms of the metric. So you relate this idea of straight lines and then these extremal distances. And from the point of view of Palatini theories, then this is a constrained possibility. So if you look at this general manifold, so you can have the metric formulation where you have where the physics of gravity is described by the curvature, which is given by these 10 functions of the metric, and of course then we have coordinate degrees of freedom. And then another possibility, also discovered by Einstein actually, is the so-called teleparallel formulation where the curvature is 0, so the space-time is flat, and the physics is carried by the antisymmetric part of the torsion, which has then 24 degrees of freedom. And it turns out that this formulation is actually completely, for the simplest actions, is completely equivalent to this formulation where the physics is carried by the curvature. And there is a third possibility where both the torsion is 0 and the curvature is 0. And we look at the non-metricity, which is the covariant derivative of the metric. So we have 40 functions here, and then the physics is carried by them. And again, for simplest formulations, this is equivalent. And the Palatini formulation that I will discuss is sort of where you don't impose any constraints. So you live in this three-dimensional or in this 74-dimensional space. And of course, then you can include both the curvature and the torsion, so you can live on this plane. You can include both non-metricity and torsion live on this plane, or you can take different hypersurface cuts corresponding to different gravitational theories. But from the point of view of Palatini formulation, all of these are just like adding Lagrange multipliers to your action, so they're not particularly natural. Why is this interesting? So I said that they're equivalent in simplest case. In particular, if the Einstein-Hilbert action or the equivalent, then you get the same physics out of it if matter is also minimally coupled, so matter doesn't couple to the connection. However, now if the gravity action is more complicated than just the Einstein-Hilbert term, or if matter couples directly to the connection, these theories are physically inequivalent. So that's why I said they're like different trees, because you start with the metric formulation, start with Einstein-Hilbert, then you add stuff, then you extend. And here instead, in Palatini, you have some starting point, and then you have different extensions. And in particular, now we come back to Higgs inflation. Recall that there was this term where you have the Ricci scalar times the square of the Higgs field. That is crucial for Higgs inflation that we'll now discuss. So this couples directly to the connection. The Ricci scalar, of course, depends on the connection. And this breaks the equivalence between the formulations. And this was realized by Bauer and Demir rather quickly after Higgs inflation was proposed. So let's see how this works. So we have here the action that I wrote down before. So here is the standard model Higgs potential. Here is the canonical kinetic term for the Higgs. Here we have the Ricci scalar, which I've now written in terms of the Ricci tensor and the inverse metric. And just note that this depends on the metric, first derivative of the metric, second derivative of the metric. And here is this coupling where we have 1 plus 𝐸h squared, and now I've taken the Planck mass to be unity, so I don't have to carry it around. So this is the metric version. And the Palatini version, the action is exactly the same, except now this Ricci tensor depends only on the connection. And note that in general relativity, the Riemann curvature tensor is defined in terms of the connection. And when and the Ricci tensor hence also depends only on the connection. This dependence on the metric comes from choosing the Levi-Civita connection. Now, if we leave the connection independent, you see that the action is actually first order in the derivatives of the connection, and the metric is an auxiliary field. So now the easiest way to compare these different models, so what's happening in the metric case, what's happening in the Palatini case, what is the difference, is to do a conformal transformation. So we just transform the metric tensor like this. And in the Palatini case, there is no effect on the Ricci tensor because we keep the connection fixed. The connection and the metric are completely independent. And it's very easy to see here what happens. You just here, this volume element here from the determinant of the metric picks a factor of f2 minus 2. That's why the potential gets a factor of 1 over f squared. The kinetic term, because it has one factor of inverse metric, it has 1 over f squared, but times f. So it's 1 over f. And then here, of course, this f, and f2 minus 2 cancel by construction. So now, this is what we get in the Palatini case. And in the metric case, then we also get derivatives of the conformal factor from inside the Ricci tensor. So the difference is just that in the metric case, we have this. So the new action, or the action in this frame where there's a minimal coupling between the Higgs field and gravity, then you get also this dependence on the derivative of f. So this is the so-called Einstein frame. So now if we solve for the connection, we just get the Levi-Civita connection in the Palatini case. So the difference that was originally in the gravity sector, that the connection is different, has been shifted now to the Higgs sector. So now we can just look at what is the Higgs doing, and then we have different evolution. In particular, we have different inflationary behavior. And if you look at the Higgs now, we have the, so this is now we have just input this. So here we had this action, this form of the action. Now we just input this f here. So f is, for large field values, goes like 1 over h squared. So in the Palatini case, it's very simple. And in the metric case, we also have this contribution from the derivative of f. But it's really easy to actually see what's happening here. Now, what we want to do is move to a canonical kinetic term so that it's easier to figure out how the field is behaving in this sort of potential. But you see that if h is very large, so if we're very far up the potential, then this goes like 1 over h squared, and this also goes like 1 over h squared. So then we have dh over h squared. So we see immediately, without doing a calculation, that the relation between this original Higgs field H and the field that has a canonical kinetic term is exponential or logarithmic, depending on which way you look at it. So now we define a new field chi that has a canonical kinetic term, and then for large field values, this old field is exponential in the new field. And now, in this case, the difference between the metric and the Palatini formulations has been transferred to this field transformation, because the potential is the same in terms of h, it's only this kinetic term that is different. So in the metric case, this old field is exponential in the new field with a coefficient of order 1, whereas in the case of Palatini, this non-minimal coupling originally between the Higgs field and the Ricci scalar appears in a square root here, and it turns out that this is of the order 10 to the 10. So we have actually exponential dependence on the new field. So what this means, and also if you look at this potential, this is the Higgs potential goes like h to the power 4 for large field values, this h squared square. So you see that this is asymptotically flat, which is very good for inflation, flat potential. So this means now that because of this, that the potential will actually be, in terms of the canonical field, exponentially flat. So in the metric case, we have an exponentially flat potential with this coefficient of order unity here, and then here we have a very large coefficient. So, and now this difference between the Palatini and the metric formulation, which started as this, you know, in a sense abstract, like do we treat the metric and the connection as independent, do we assume the Levi-Civita connection, is now translated into predictions for the CMB via this inflationary potential. So in the metric case, the prediction for the spectral index in inflation is 0.96, and the tensor to scalar ratio, which says what is the ratio, what is the ratio of the amplitudes of the gravitational waves to the scalar perturbations, is about 5 times 10 to the 4, and these are both predictions. So the only thing that is actually fitted is the amplitude of the CMB, fluctuations 10 to the minus 5, which then fixes that this psi is about 10 to the 4 times square root of lambda, and this is lambda is the quartic coupling of the Higgs, which on inflationary scales is maybe 10 to the minus 2 or 10 to the minus 3 or something. And in the Palatini case, the spectral index to leading order is the same. The difference is the tensor to scalar ratio. So here it's 5 times 10 to the minus 3, which is within reach of the Simons Observatory, the CMBS-4 experiment, the upcoming Lightbird experiment. And here, tensor to scalar ratio is of the order typically 10 to the minus 11 or something like this, which could not be measured with any foreseeable technology. So if we compare these predictions now to experiment, so this is the Planck 2018 results. This is the primordial field of the spectral index. This is the tensor to scalar ratio. So now the Higgs inflation in the metric formulation is here, actually basically in the middle of the observational constraints. And then the Palatini case is the same, except it's right here on the lower line. So the R is so small that you would never see. So, and if you look only at this prediction of inflation, things look very nice, because this is a very simple model in the metric case. And now you say, okay, it's metric or Palatini. Now you just do the look at the upcoming results for this tensor to scalar ratio R, which reached to 10 to the minus 3. And if it's detected at this 5 times 10 to the minus 3, that's of course strong evidence for this metric Higgs inflation. If it's not, then you know that it's not metric Higgs inflation, but maybe it's the Palatini. However, there are some complications to the story on the particle physics side, and as I will want to discuss also on the gravity side. So if you look at these actions that I wrote down, where we have the kinetic term, the potential, and all of the difference between the metric and the Palatini cases is in these kinetic terms. Then you see that the non-luminous coupling introduces new scales, in the sense that when h is very small, then this factor goes to 1, this factor goes to 1, and then you're back to the standard model Higgs. So when the field value is small. When the field value becomes larger, then you start having new behavior, like this inflationary, like this asymptotically flat potential during inflation. And if you look at this, when do you start seeing this new behavior? Then in the metric formulation, you see that when h is of order 1 over psi, then you start having something here. This term becomes important. And here there is the only, and there is also another scale, 1 over square root of psi. And of course, M-Planck has been suppressed. So basically there's this new physics at 10 to the 14 GeV, and then something also happening at 10 to the 16 GeV. In the Palatini formulation, the only new scale is m-Planck divided by square root of 𝐸, which is parametrically higher, but because 𝐸 is larger, it's actually in terms of 𝐺eV about the same scale. Now, what this means is that the oops, sorry. Oh, I have to. There's some problem with the screen sharing. Let me try again. Okay, now you should be seeing. Let's just check what's going on. Okay, so what's happening here is that recall that this physics was originally in the coupling, non-nominal coupling between the Ricci scalar and the Higgs. So when this non-nominal coupling 𝐸 is large, whether it's 10 to the 3 or 10 to the 8, in the metric and the Palatini cases, then this non-nominal coupling between the Ricci scalar and the Higgs field starts being important. So this means that essentially you're seeing enhanced gravitational effects. And so usually you think, okay, if I don't have the non-nominal coupling, then I have the standard model Higgs and other parts of the standard model, and I have the Einstein-Hilbert term, and this Einstein-Hilbert term starts being important if, for example, if you look at particle scattering only at the Planck scale. That's not the case here. This 𝐸 brings these gravitational effects to lower scales. And you see that perturbative unitarity is violated at 3 level on the scale of m-Planck divided by 𝐸 in the metric case, and in the Palatini case on this case. And in the Palatini case, the unitarity is not lost until the inflationary scale. In the metric case, it's strongly background dependent. So if you are on Minkowski vacuum, you would see new physics or maybe strong coupling at 10 to the 14 𝐺eV. But if you're on the inflationary scale, then actually this perturbative unitarity violation is pushed up. So we have particle physics effects. This is just the scattering of particles in the Higgs doublet that have new interactions that have a gravitational origin that's been transferred by the conformal transformation. So the choice of which formulation of gravity you use, metric or Palatini, affects particle physics considerations like unitarity. And if you did this calculation, not in the Einstein frame where you have this minimal coupling, but in a frame where you have non-minimal coupling, then in fact you would see that this W, if you consider for example W on Z scattering, then you would see that you have a contribution from gravitons there that starts being important. So you could really see that this is a gravitational effect. So the coupling to particle physics brings the quantum gravity scale down. So this is a problem if you think that when you use perturbative unitarity, you can trust your theory anymore, you don't know what happens. On the other hand, it can be an opportunity because now you might have a possibility of seeing these effects related to quantum gravity on smaller scales. By the way, I didn't ask at the beginning, do you take questions only at the end, or should I encourage people to ask questions also at some intervals in the talk?
But, we generally ask questions at the end.
All at the end?
Yes, at the end.
Oh, okay, good. Then, okay. So this is, just considering now what happens with this Einstein-Hilbert term. So what I have there is just, I take the same action, and then I just look, is it metric or Palatini? But as I mentioned, the extensions are also different. And the space of gravitational theories in Palatini is much larger than that of the metric theory. And if you think about it, you have two new tensors. You have this non-metricity tensor that has 40 degrees of freedom, the torsion that has 24, so you have 64 new degrees of freedom. And also, if you look at it in terms of counting dimensions, then these are dimension 1. So if you contract this with itself, square it, that's dimension 4. But you can contract this with this, and you can take different contractions, and they have 3 indices. So you can actually, even just playing with these, you have lots of new possibilities. So they have two different things. The same action can give different physics depending on which theory of gravity you're in, like the Higgs inflation case, and then you can have extensions. And one instance that we've studied that I will just briefly mention, I don't want to talk about it in detail, is the case when you have, instead of the Ricci scalar, you add the square of the Ricci scalar. So this was already a feature of the first inflationary model proposed by Starobinsky in 1980. In the metric case, this gives you an extra scalar field, effectively. In the Palatini case, this is not the case. There's no new degrees of freedom. This R square just reduces to tensor to scalar ratio without having any other changes. So if you have an inflationary model where the tensor to scalar ratio is too large, you can just say, let's switch to Palatini, add this R square term, and then you're fine. So let me discuss briefly some of these extensions of GR and how they look in this Palatini case. So there are many, many terms that can be constructed with this. And ones that I found particularly, we've looked at some that are particularly motivated, in particular those that are only dimension 4. Of course, if you go to higher dimensions already in the metric case, you have lots and lots of terms. And one is the coupling the Higgs term to the Holst and the Ні-Young terms. So the Holst term is just the contraction of the Riemann tensor with the Levi-Civita tensor. So in the metric case, this is 0, because in the metric case, if you antisymmetrize the Riemann tensor in the last 3 indices, you get 0. This is not true in the Palatini case. So when you write your action from the point of view of effective theory, there is no reason to leave this out. This is dimension 2. This is the same dimension as the Ricci scalar, and the only difference is that there you contract with the metric, here you contract with this Levi-Civita tensor. So we added this, so we can multiply it by some constant, and then you can also couple it to the square of the Higgs field. And then we also consider something called the Ні-Young term, which has been of interest in loop quantum gravity, which is the contraction of the Levi-Civita tensor and then the covariant derivative of this torsion tensor. And this is, of course, a boundary term, so it only you only get something if you couple it to the Higgs field. Again, this dimension 2, so this term is dimension 4. So if you just add these terms and then you see what happens, then you expand the range of inflationary predictions a lot. So this is, again, the spectral index. This is the tensor to scalar ratio, and this is a scan over these couplings, and this color indicates the value of the non-minimal coupling 𝐸. So the nominal coupling between the Ricci scalar and the Higgs field. So this star is the prediction of the metric formulation, n is about 0.96, and this R is 5 times 10 to the minus 3. This line is the Palatini case, so the answer depends on the value of 𝐸, but reasonably you're like somewhere here, because to choose a very small value of 𝐸, you have to also have a very, very small value of the Higgs quartic coupling, which is very tuned.
Hello, can I ask
yes.
a question? So I was wondering that there are also other formulations of gravity, like the chiral formulations and the Einstein-Cartan formulation, where you don't bring the Ricci scalar in the forefront, but you deal with the curvature of the spin connection and write the action in terms of the curvature of the spin connection. So is this study being carried out in any other formulations other than the one you described, or has it not been carried out yet?
Okay, so so there are two different things here. One is Einstein-Cartan. So in other words, what are the degrees of freedom with regard to to have the torsion, to have the non-metricity, and so on. So Einstein-Cartan refers to this theory where you have both curvature and torsion, but the non-metricity is 0. Then there is another question of what is the what variables do you use to describe these degrees of freedom? So for example, so here I'm discussing in terms of the metric and the affine connection. You can also discuss this in terms of the spin connection and the tetrad. But the spin connection, the tetrad, doesn't bring anything new.
Okay. Okay.
So in this case, for example, the teleparallel case where you have where the curvature is 0 is actually much more convenient to describe in terms of the tetrad and spin connection, and we did this. So we discussed Higgs inflation in that case. Although one could also discuss in terms of the metric and the connection, but it's just more complicated. But this question of metric versus tetrad is not a physical question. That is just a question of what are convenient variables to describe your physics.
Okay. Okay. Thank you.
Yeah. So here we just add these terms, and you can even put psi to 0. So you don't. That's this line. So you don't need to have a normal coupling to the Higgs. Between the Higgs and the Ricci scalar at all. The point of this plot is just to show that this what appeared to be a very nice clear prediction at 3 level from Higgs inflation. When you include these gravitational terms, actually you get a much wider spread of predictions. With these terms, you cannot get anything. So if you would find that the R is 10 to the minus 8 and spectrum is 0.965, this is something that is impossible to get. Or if you would find that, well, okay, or other combinations on this plane. And you also get a bit similar spread if you include loop corrections in the metric or the Palatini case, so that they also widen this spread because that was only 3 level. But I here want to concentrate on this gravitational case. And one can also include other terms, and we did. We just recently published a paper when we look at the John-Simon's term, and then you can see what happens to the inflationary predictions then, and so on. But I want to discuss a bit different tack. So this is something we did with Joseph Verbin, who had the idea. He had the idea that what if we take this Palatini idea and apply it to electromagnetism and see what happens. So the basic idea of Palatini is that instead of having only the metric that it then determines the connection, you have metric and the connection as independent variables. But we can also do that for gauge fields. So usually the field strength, so now forget about gravity, we just think about U1 gauge theory, just think about electromagnetism. And so usually the field strength F alpha beta is just given by the antisymmetrized partial derivative of the gauge field. It's in a similar way as the connection is fully determined by the first derivative of the metric. But we don't need to do this. We can keep the field strength and the gauge field independent variables in the style of Palatini. And they may be earlier, but the earliest I found was the use of this was from Fadeev from 1969, who formulated QED in these terms. The new twist that we had was to add non-minimal coupling. So do the same that was done in Higgs inflation. You have the metric and Palatini are equivalent. If you have just minimally coupled matter, Einstein-Hilbert. If you have non-minimal coupling, things are different. So we thought, okay, let's do the same here for the electromagnetic case. So let's go first go through this normal electromagnetic case when we don't have non-minimal coupling. So then the action is this: you have F alpha beta, and then minus this minus the antisymmetrized partial derivative A coupled to F alpha beta, and these are independent variables. So now if you vary, of course here you get just F alpha beta from here times 1/2. Here you get minus this, so you immediately see that you get the this solution, usual solution, and you insert it back into the action, you get the usual action. And Fadeev used this form of the action to formulate QED, because now your action is linear in the first derivative of the dynamical variable, and you don't have squares of first derivatives. So treating the constraints becomes much simpler. And in fact, he showed that this is completely equivalent at all loop orders to the usual formulation. And this is the same way as in if you take the Palatini formulation or the Einstein-Cartan formulation, and you just have the Einstein-Hilbert action, then you vary, you have the equation of motion for your connection, you find, okay, the solution is 𝐬𝐵 connection. Now, if we couple this F alpha beta to a scalar field, we break the equivalence between these formulations. So this was our new thing. So in the similar way as in the gravity sector, you have the metric is the your field. Here we have corresponding gauge field. And in the Palatini case, we have the connection. Here we have alpha beta. And in the metric case, the connection just reduces. So this ring denotes the 𝐬𝐵 connection. So we just have the connection determined in terms of derivatives of the metric. Here also F alpha beta just reduces to this. And in the Palatini case, in the gravity side, we have a change in the symmetric parts of the connection. The 𝐬𝐵 connection is, of course, symmetric. And then we have an antisymmetric contribution, which does not exist in the metric case. And similar way here, the antisymmetric part of F will change, but we also have a symmetric part of the field strength, which does not exist in the usual formulation. And the new parts, so the antisymmetric part of new antisymmetric part of F and the symmetric part are determined by the scalar field by this non-minimal coupling, and then eliminating F, so solving it, inserting it back into the action, gives you a modified scalar field action. So let's see how this goes. So here we have the gravity into the mix. So we have Ricci scalar, some scalar field, could be the Higgs, with minimal kinetic term and some potential. And then here we have these two terms that we had before for the gauge field, except we added non-minimal coupling B phi here. And now we can also take the trace of F alpha beta. Note that F alpha beta is dimension 2. So we can have phi squared here, non-minimal coupling, and still be dimension 2. And usually, of course, this would be 0 because usually F is antisymmetric. Not so here. And then we can couple F alpha beta to kinetic term, and this is already then dimension 6. And in the paper, we have more terms written down, but this will suffice to give you the idea. If you solve for F alpha beta, I mean, you can basically do it in your head while watching this. You just vary with respect to F alpha beta, you get this antisymmetric part. For the antisymmetric part, you get this, and then here one factor of B times the antisymmetric part. So when you equate them, you have antisymmetric part equals B times F. So basically, you have this, that the antisymmetric part is just the usual one, except we have this coupling function here. For the symmetric part, we get the symmetric part here. Here we get G, and here the kinetic term. So then the symmetric part is given by the metric, and then the kinetic part of the scalar field. We insert back into the action, and then we just get something that depends only on the scalar field, and then this kinetic term. So for example, this G alpha beta term, if you contract with itself, it will give you, here you see C squared divided by B. So you get an additive contribution to the potential. You contract this with this, you get a contribution to the kinetic term. So basically you get some function of the field in front of the kinetic term, and you get a new form in the potential. Now the question is, what can you do with this? And it turns out that similarly to Higgs inflation, where this non-minimal coupling changes inflationary dynamics in an interesting way, that's also the case here. Also, whether this is equally interesting, I think is a matter of opinion. But one thing that this does solve, and I'm not going to show it, I'll just mention it, is that in usual scalar field theory, the problem is that, let's say you start with the Higgs, and the potential has term like phi squared, and then phi to the 4th. And now you can ask, what about phi to the 6th? And of course, this is not renormalizable, but in terms of effective field theory, we expect that these sorts of non-renormalizable terms would also be present, phi to the 8th and so on. And in inflation, it's a problem because then typically if you have lambda phi to the 4th, phi squared or so on, then the field is very large, of the order of Planck scale or larger. So these higher order terms are not really suppressed by anything. So, and then the potential gets these higher and higher terms. The flatness of the potential is spoiled, so you don't have this flat potential that you need for inflation. Here, this problem is solved. If we include not only these terms in the potential, but also in the coupling functions, which makes sense. Let's say, let's consider our action to dimension D, and we write all of these terms up to dimension D. then it turns out that the potential becomes steeper and steeper, but at the same time, the kinetic term has a stronger and stronger dependence on the field, and these compensate each other so that the leading term in the potential is 2d divided by d minus 2, and d is the mass dimension up to which you go. So you note that as you make it higher and higher, d higher and higher, this goes to chi-squared, which gives a completely acceptable tensor to scalar ratio. Completely acceptable spectral index. There is no problem of having with the flatness of the potential. Unfortunately, the tensor to scalar ratio is still too high, but the flatness problem is at least solved. And then if we combine this with Palatini gravity, so if you have normal coupling also to the Ricci scalar, we could maybe improve the stability of Higgs inflation, because Higgs inflation also has this problem that if the potential is not 5 to the 4th, but it has 5 to the 6th terms of normal coupling, includes higher order terms, then the predictions are very sensitive. And this is something that me and my PhD student 𝐬𝐵 are looking at. Okay, to conclude, Higgs inflation, it's very minimal bottom-up scenario for particle physics and gravity, where you use only the known degrees of freedom, but you include new terms that change the behavior of these degrees of freedom. And these terms, in terms of effective field theory, you should include. And in the Palatini formulation of general relativity, non-minimally coupled matter acts as a source in the connection equations of motion, because the connection has its own equation of motion. And this then breaks the equivalence between different formulations of GR, because then you don't just get the Levi-Civita coupling, you get something else. I mean, we did this in this case by doing a conformal transformation, but you could also solve for the connection and insert back into the action, and then you see if the connection depends, in the Higgs inflation case, on the Higgs field. And in particular, Higgs inflation includes this term that couples the square of the Higgs to the Ricci scalar. So necessarily, when breaking this equivalence between the formulations, and then also bringing, if you use it for inflation, the gravity scale down, so that you could see something interesting well below the Planck scale. The theory space of different gravity theories is not fully mapped, and even in the case of Palatini, which is one of the simplest formulations, the space of which sort of actions are stable, so which give you viable theories and what kind of behavior do they have, is not fully known. And this is something we have also been looking at. And then finally, it's also possible to take this philosophy and apply this Palatini formulation, so making the field and its connection or field strength independent. You can apply it also to gauge theory. But I think that's probably all I wanted to say, so I'm happy to take questions.
Okay, so if the audience has any questions, please unmute yourself and ask.
So I want to ask another question. So I was wondering that you said that if you bring the tetrad or the connection in place of the metric, then it would not give some other insight of physics. It is just a change of formulation. But I was wondering that these chiral theories of gravity, for example, the chiral Einstein-Cartan, when they are studied in using quantum field theory approach, then it gives rise to different results in the divergences, and at least in the one loop and the two loop divergences. So I was wondering if this kind of theories can shed some more light about these studies, or when you couple Higgs to these gravity theories.
I'm not familiar with this chiral theory. Can you briefly explain what it is? What's the construction?
So in the chiral theory, in the usual theory of gravity, when you have the tetrad of the connection, you use the full curvature of the spin connection. But in the chiral theory, you use the self-dual or the anti-self-dual parts of the spin connection,
Right.
and then construct the curvature out of it, and then formulate the Lagrangian of the theory. So it is seen in some papers that if you use these chiral theories, then the renormalization flow is different. The divergences coming up at one
Right.
loop are different than the Einstein-Hilbert action. So I was wondering that if it can shed some light to what you are studying. I mean, coupling Higgs to this gravity and then studying these things.
Yeah, I don't know, because I'm not familiar with the theory. There are different formulations, but I think it would probably I would guess that it might be possible to also formulate that in terms of the metric and the connection. But of course, there are different formulations suggest different different physics and different ways of doing things. So for example, if you look at the teleparallel formulation of general relativity, which is where you have the curvature is 0, non-metricity is 0, you have only the torsion, then you can do it in terms of the connection and the metric, but it's much more transparent if you use the tetrad and the spin connection, and then also maybe doing generalizations is easier there. So I would say that there the theory you describe is not whether you use the spin connection or not, but it's a different formulation. So using different parts of the using different parts of curvature / metric / tetrad / spin connection as your independent degrees of freedom. But I'm not familiar with that, but it's possibly interesting.
Okay. Thank you.
Okay. There is any other question? Okay. If there is no other question, I have a question. I have a point actually. First thing is that probably 𝐸𝐵 has already a paper probably with Higgs inflation and Einstein-Cartan gravity. Probably in 2020, if I'm not wrong.
Yes. So we wrote a paper and then their paper appeared quickly afterwards.
Okay. Okay. I have just a simple question. So we consider first thing is that this comparison with the 𝐸1 gauge bosons in this comparison you showed, it was really interesting. And my question is that we consider this non-minimal coupling to make the potential flat only.
Yeah. So we did this. So we basically had this, and then what can we do with it? And and the only sort of useful application that I saw for inflation was to make the potential flat. But one could potentially also do other things with it. And one can, of course, also then extend this to higher order. So there are these theories, for example, called fractons, where you have essentially a gauge field that has two indices, and you can extend the construction there and see what you would get from there. But I didn't immediately see any other sort of application of this immediately for the stuff that we did, other than to improve the stability of the potential to corrections. But that doesn't mean that there are no others.
Okay. And
to also add to this Einstein-Cartan, so let me just note that so Einstein-Cartan is the theory where you have metric formulation and torsion. So that's basically when you live on this plane here. If you have only the Einstein-Hilbert term, it doesn't matter whether you are Einstein-Cartan or if you have even, let's say that you have this form of the action, then whether you put the non-metricity to 0 or the torsion to 0, but include also the curvature, then it doesn't matter. So whether you have this full Palatini, whether you have Einstein-Cartan, the result is the same. The new thing that was done here, first by us, and then very quickly afterwards, I mean, we were working at the same time, we just put our paper first, was to have this Nian term and the Holz term that we both studied. If you don't include those, then there's no difference between Einstein-Cartan and this full Palatini.
Okay. Thank you. So is there any question anymore from the audience? Okay. If there is no other question, so let us thank again the speaker for this interesting talk. And
thank you for the invitation.
Thank you for that.